Welcome, curious minds. We're diving deep today into something pretty exciting, maybe even a quantum leap in computing.
Definitely feels like that sometimes.
Yeah. You've probably seen the headlines about Rigetti Computing and their big announcement.
hmm
So our mission today is really to unpack what this milestone actually means. Not just for Rigetti, but for where tech is heading. And for you, our listener, who wants to get these complex shifts, like quickly and thoroughly.
That's right. And it's worth remembering, when we talk quantum computing, it's fundamentally different from the computers we use every day, right?
Right. Bits versus qubits.
Exactly. Classical bits are just 0 or 1. Simple. But quantum computers, they use qubits. And thanks to quantum mechanics, weird stuff like superposition, entanglement, these qubits can be 0, 1, or kind of both at the same time.
Which changes everything for certain projects.
Totally changes how you process information. It opens the door for potentially, way faster calculations for specific, very complex tasks.
Okay, so let's get right to it. The Rigetti news. They announced hitting a mid-year performance goal, 99.5% median two-qubit gate fidelity.
Yep.
On a modular 36-qubit system. Now, that number, 99.5%, it really jumps out. Why is that percentage, and the fact they basically cut their error rate in half, why is that such a big deal?
Yeah, it really moves the needle, that 99.5%. The key takeaway is that they halved their error rate.
Okay.
Think of it like, I don't know, building something intricate with slightly wonky Lego bricks. Every connection you make, every extra brick, it just multiplies those little imperfections.
That's right. Errors add up fast.
Exactly. So having the error rate means you can string together like twice as many operations before the whole calculation just falls apart from accumulated errors.
Okay. So you can tackle more complex problems.
Precisely. It gets us closer to this idea of fault-tolerant quantum computing. That's kind of the holy grail.
So this isn't just tweaking a number. It's a real step towards qubits that actually, work long enough to do something useful. Huge deal.
Absolutely.
And they did this on a modular 36-qubit system you mentioned.
Right.
That's out in Berkeley, California.
Indeed. It's modular, which is key for scaling up later. And Rigetti uses superconducting qubits. Their CEO, Subodh Kulkarni, he's pretty bullish, says they're like over 1,000 times faster than other methods like ion traps or neutral atoms.
1,000 times faster.
Yeah, that's the claim. And they believe that speed is crucial for scalability.
And the engineering just sounds wild. This hardware has to be cooled by something called a dilution refrigerator.
Oh, yeah.
Down to 1/100th of a Kelvin. That's, what, hundreds of times colder than outer space?
It is. Absolutely frigid. It just shows you how incredibly delicate these qubits are.
Right. Why so cold?
Well, they need extreme isolation from basically any environmental noise, heat, vibration, stray magnetic fields, you name it. Anything can disrupt their quantum state, what we call coherence.
Coherence. Got to keep them coherent.
Exactly. That ultra-cold, ultra-quiet environment is essential to preserve coherence long enough to actually compute something. It's really an engineering marvel.
No kidding. I can barely keep my coffee hot. Okay, so how does this progress on the 36-qubit system relate to their bigger machine, the 84-qubit Anka-3? Are they connected?
That's a really good question to clarify. So the Anka-3, the bigger one, they'd previously reported 98.6% fidelity, but that was specifically for a type of operation called an I-swap gate.
Okay, different measurement, kind of.
Sort of.
Yeah.
This new 99.5% milestone, that's on the smaller modular 36-qubit system, and it represents that halving of the error rate on that platform. So Anka-3 has more qubits, yes, but this 99.5% shows they're making real strides in improving the control and reliability of their underlying tech.
Gotcha. And I-swap, that's just a fundamental building block.
Yeah, it's a basic two-qubit gate. It essentially swaps the quantum states between two qubits. You need operations like that for complex algorithms.
Okay, that makes sense. So the tech's moving forward. The market must have noticed, right? What happened with Rigetti's stock, RGTI?
Oh, it noticed. All right, big time. The stock jumped over 30% right after the announcement, hit around $16.57 a share.
Wow.
Yeah, that was a 6-month high for them. And it's up like roughly 170% from its low point back in January. Investors were definitely buzzing.
So it sounds like the market perception was, okay, practical quantum computing is coming, and soon, not decades away.
That seems to be the narrative they jumped on. Yeah, this progress felt tangible.
But is that the whole story? Because I'm looking at Rigetti's actual financials, and they don't quite scream commercial product launching tomorrow.
Yeah.
Is there a reality check needed here?
You're right to ask. That's the core tension. This technical win is undeniable. It's great progress, but sources are pretty clear. It doesn't immediately translate into commercial viability or revenue growth.
Okay, what are the numbers?
Well, Rigetti reported only $1.5 million in revenue for Q1, and that was actually down 52% year over year.
Oh.
Yeah. And their operating losses were over $21 million, plus their price to sales multiple, nearly 350.
Whoa, that sounds frothy.
Speculative froth is the term used, yeah. Most analysts still think meaningful commercial use, actual revenue generation for Rigetti is likely, 3 to 5 years out, maybe more.
So, huge technical step, but the business side, still a long road ahead.
That's the picture right now. Progress, yes. Profitability, not yet.
Okay, so Rigetti's making moves, but who else is playing in this sandbox? We hear about the giants, Cisco, IBM, Microsoft, Google. It sounds like a quantum arms race.
Yeah.
How does Rigetti compare?
It's definitely a crowded field, and yeah, arms race isn't far off. When you look at Rigetti's Anka 3, okay, 82 or 84 qubits, roughly 1% error for 2-qubit gates, and coherence times around 20-ish microseconds.
Coherence times, that's how long the qubit stays quantum, right? Before it passes.
Exactly. T1 and T2 times. Longer is better, means you can do more complex stuff. Now, compare Rigetti's numbers to, say, IBM's Heron R2.
Yep.
That one has 156 qubits and a much lower 2-qubit error rate, 0.371%.
That's quite a bit lower.
It is. Or look at Google's Willow chip, Hatch-2, 105 qubits and an even lower error rate, 0.14%.
Wow. Okay.
So, the folks on Reddit who watch this stuff closely, they often point out that while Rigetti's improving, their current numbers are, quote, far worse on some key metrics. They see IBM and Google as way ahead right now, especially on error rates and maybe coherence.
That definitely adds perspective. It's not just about qubit count. And there's IonQ too, right? Another big name.
Absolutely. IonQ uses a different approach, trapped ions. Their projected tempo system aims for 100 physical qubits, targeting a really impressive 99.9% 2-qubit fidelity.
99.9%. It's another big step up.
Yeah, and a pretty fast 300 microsecond 2-qubit gate speed. But what really stands out with IonQ is their reported coherence times. Their existing Forte system, for example, T1 times around 100 seconds, T2 around 1 second.
Seconds compared to microseconds. That's a massive difference.
It's a whole different ballpark, which brings us to this sort of fundamental debate in the quantum world, Is this technology still far, far away from being genuinely useful for practical problems, like some people argue based on these performance gaps? Or is it better to think of this as an crucial experimental stage?
Like building the foundation.
Exactly, like maybe building novel things, demonstrating that you can scale, even if it's not perfect yet. Kind of like those early 3D graphics engines for games.
Right. They weren't amazing at first, but they showed what was possible.
Precisely. They weren't immediately making billions, but they were the essential groundwork for the huge gaming industry we have now. So there's this real tension, between wanting immediate results versus making that necessary foundational progress.
Interesting analogy. Okay, let's zoom out a bit. Beyond just Rigetti or IBM, the UN has designated 2025 as the International Year of Quantum Science and Technology. That sounds like a pretty big signal, doesn't it?
It's huge. It shows this isn't just a niche academic thing anymore. There's global recognition, surging investment, and breakthroughs seem to be happening faster and faster across the whole field.
And the market forecasts reflect that.
Oh, absolutely. The numbers are kind of staggering. The overall quantum tech market could hit, maybe $97 billion by 2035?
$97 billion.
Yeah, with quantum computing specifically grabbing somewhere between $28 and $72 billion of that. And looking further out, maybe $198 billion total market by 2040. That shows enormous long-term confidence.
And you mentioned investment surging. Where's the money coming from?
It's pouring in. In 2024 alone, something like $2 billion went into quantum tech startups.
Yep.
That's a 50% jump from the year before.
Wow.
And what's interesting is that a big chunk, about 34%, came from public funding. Governments are getting serious.
Like strategic investments.
Definitely. You see huge commitments. Japan putting in $7.4 billion. Australia giving $620 million just as a quantum. Illinois planning a $500 million quantum park. Singapore investing $222 million. It's clear governments see this as strategically vital.
Okay, and you said quantum technology, not just quantum computing. What else falls under that umbrella?
Right, good point. It's really three main pillars. First, there's quantum communication. That's all about securely transferring quantum information.
Like unhackable communication.
That's the dream. It's projected to be a $10 to $15 billion market by 2035. A big piece of this is post-quantum cryptography, PQC. Basically developing new encryption that even a powerful future quantum computer couldn't break. Getting ready for Q-Day.
Q-Day. Sounds ominous. Okay, communication is one pillar. What else?
Second is quantum sensing. This is about creating a whole new generation of incredibly sensitive sensors.
Sensors for what?
All sorts of things, measuring gravity, magnetic fields, time, temperature with unprecedented accuracy. We're seeing examples like NASA putting an ultra-cold quantum sensor in space, or QCTRL using quantum magnetometers for navigation where GPS doesn't work. Sandbox AQ is even using AI with quantum sensors for navigation.
Fascinating. So communication, sensing, and the third is computing, which we've been focusing on.
Exactly.
But for computing, especially as we try to build bigger machines, isn't there this massive elephant in the room?
Yeah.
Errors.
Yes, error correction. It's gone from being like a theoretical nice-to-have to absolutely essential, hasn't it?
Seems like it. As you add more qubits, the errors just multiply, right?
Uh-huh.
So what's happening there?
Well, it's a huge focus now. You can't just ignore errors anymore. We're seeing progress from the big players like Google with their Willow chip demonstrating some techniques. And there are startups like Alice and Bob or Riverlane entirely focused on building error-corrected quantum computers from the ground up. It's a massive challenge, but people are tackling it head-on.
Okay, so error correction is key. Now, think about all these pieces: communication, sensing, computing, plus things like AI.
Yeah.
How do they fit together? Are there synergies?
Oh, absolutely. That's where things get really interesting, I think. Quantum tech doesn't exist in a vacuum. It connects powerfully with other fields. Think about AI and machine learning.
Okay.
AI could help us design better quantum hardware faster. And conversely, quantum computers might revolutionize how we train massive AI models someday.
Interesting feedback loop. What about robotics?
Robotics could benefit from all three quantum pillars. Quantum sensors for incredible precision, quantum communication for secure control networks, maybe even quantum computing for complex optimization problems in manufacturing.
Right. And sustainability, climate change.
Big potential there, too. Discovering new materials for catalysts or batteries, modeling complex climate systems more accurately. Quantum could be a game changer.
And cybersecurity, obviously. Both a threat and a solution.
Exactly. Quantum computers pose a future threat to current encryption. That's the Q-Day risk. But quantum communication offers new security like quantum key distribution, and PQC aims to provide defenses. It really cuts both ways. So, it makes you wonder, what kind of aha moments could these convergences spark in your own field, listener?
Good question. So let's try to wrap this up. We started with Rigetti's technical win, that 99.5%
It's a
fidelity.
real achievement.
Saw the market get really excited, maybe a bit too excited, given the financials.
A dose of reality there, yeah.
Yeah. We compare them to the giants like IBM and Google, saw the different approaches like ion Qs, and touched on that how far away is it really debate. And then broadened out to the whole quantum tech landscape, communication, sensing, the funding boom, the global race. It's moving fast.
It really is. I think the key takeaway is, commercially viable quantum computing for widespread use is still likely some years off. No denying that.
Right.
The fundamental breakthroughs, like the fidelity improvements we discussed, the massive surge in investment, and all this progress in the other areas like communication and sensing, it all clearly shows quantum tech is rapidly shifting from just theory into, well, something much more tangible. It's becoming real.
Okay, so one final thought to leave everyone with. I saw this definition on Reddit. Kind of interesting. Intelligence is effective information processing.
Okay. I can see that.
So if quantum computers, even just for specific tasks, can process information potentially millions of times more effectively, what does that imply about our definition of intelligence, about what becomes possible in the next few decades, especially if, AI starts helping improve these quantum systems recursively?
That's a deep thought to end on. Where could that lead?
Exactly. So maybe something for you, the listener, to mull over. What parts of your world, your work, your life could be totally transformed when these quantum capabilities really start to mature?